Good evening, students. My name is Shashank, and we are doing a crash course on chemistry for the upcoming JEE exam of 45 days. And today is our second day for the coordination compound. So, in the previous class, we mainly discussed about the IUPAC nomenclature and all. Then we studied about the isomerism that exists in the coordination compound. So today we will be covering this left of topics, which are bonding, mainly about bonding, and about the coordination compound importance. Okay. So let us start. So these are the topics that we will cover today: the valence bond theory, tetrahedral complexes, and all. So you can have a look at this. So let us start. So you already know the weightage. So first of all, we will start from the valence bond theory. So valence bond theory is mainly based upon the hybridization concept. So you must have studied this hybridization concept in the chemical bonding chapter. So it basically deals with the say hybridization concept using the valence orbitals of both the ligands and the coordination metals or the metals that we are having at the central atom. So we will have the valence shell of the ligands and the metals. Now, there are certain hypothetical steps that are considered that happens during the formation of a coordination compound. So, if we are using this valence bond theory, we perform means we keep in mind that we are performing some hypothetical steps, and these steps are not in real. Okay, so let us see this step first of all. So first of all, the whenever a ligand approaches a metal ion, then the valence orbitals of the metal ion they rearrange or you can say combine to give hybridized orbitals. So it's the similar case using the similar case that we used in the hybridization concept of the say chemical bonding and all. Here we are what we are doing is that we are taking the valence orbitals or valence shell and using the orbitals present in the valence shell to make hybridized orbital. What are hybridized orbitals? So they are such orbitals which have the same energy and same shape. Okay, so this is the case. So they have the same energy and the same shape. So first of all, whenever a metal, say ligand approaches a metal, this happens. Now, the type of hybridization means say whether it is sp2, sp3, d2, sp3 or sp3, t2, it depends upon the nature of ligand. So it is mainly dependent upon the nature of the ligand. So although this valence bond theory does not account for the ligand, but we will know very well that say if we are talking about inner orbital complexes or outer orbital complexes, then it is mainly dependent upon the nature of ligand. But valence bond theory does not have account for this. So this can be considered as the first limitation of this valence bond theory. Now next, after the hybridization take place, means the hybridization of the metal ion takes place. Now the ligand donate a pair of electrons. Okay, so each donor side donates a pair of electron. So sub pair of electron means two electrons simply. So two electrons. Now in the next step, we have the structure. So after this ligands have donated this say electrons, we got some structure. So it can be tetrahedral or say it can have octahedral, square planar. So depending upon the hybridization that we have, on the type of hybridization, whether it is sp3 or dsp2, we have different kinds of shape and structure. So let us first take a look at the square planar and tetrahedral complexes. So both square planar and tetrahedral complexes have a coordination number of 4. Okay, so they both have a coordination number of 4. Now let us take an example of NiCN4 2 minus. So if so first we have to find the oxidation state of Ni here. So if you have attended the first class, it is done like this. So suppose we do not know the oxidation state of Ni, then it will be taken as X. Now this one Cn has a charge of 1 negative. We know very well that it is a ligand with a negative charge on it. So there are 4 of this. So 4 into 1, which will be 4. And the net charge on this complex is 2. Okay, so this is minus 2. So what will be the charge on the metal? So it will be 4 minus 2, 2. So we have a Ni2 plus ion. Okay, so we have a Ni2 plus ion. Now we know that nickel has a outer configuration of this D10. Now since 2 electrons are removed from it, then we will have this D8. Okay, so we will have D8 configuration and 3D8 specifically. Now what happens is that this upon the approach, so this is Ni2 plus. Now what happens is that, so we are removing 2 electrons from here. So 2 electrons are removed here, and we are remained with this 8 electrons. Okay, so this is the case. Now this electron get paired here. This goes here and gets paired. Now we are left with one d orbital, which becomes vacant here, one s orbital, and 3 p orbital. Now we know very well that since we are having 4 CN4, so we will require 4 vacant orbital for that. So it hybridized like this. So we are taking 1d, 1s, and 2p orbitals. So total we have a hybridization of dsp2. So this is the hybridized orbital, the set of hybridized orbital that we have here. Now we have 4 CN, so each CN will donate one pair. So these are the 4 pair of electrons that are donated by 4 CN ligand. Now since we have a hybridization of dsp2, then we will have a shape as square planar. So we will see later on that what different hybridization results in different kinds of structure. Now let us take another example here. Okay, so let us take another example. Okay, Akshita Sharma. So you can just take the screenshots of this say slides, and you can just revise from this only. So it is sufficient for your preparation. So you can take it as a revision note also. Okay. Now let us move to another example, that is high spin complex. So specifically we are talking about high spin and low spin only, but I have not, since I have not cleared about it. So we will take for granted that okay, we do not know, it is just an say in case of valence orbital theory, it is an experimental data. So here we have this NiCl4 2 minus. Now just we are changing the ligand from cyanide to chlorine. Okay. So what we will do here is that since chlorine is a weak ligand, so we will study about this weak and strong in the upcoming say CFSC theory. But for say it does not pair the electrons, so we are not having any pairing of electrons. These 2 electrons remain as it is, and now we need 4 vacant orbitals. So these are the available 4 vacant orbitals. So the hybridization becomes sp3. Now each Cl minus donates a pair. So these are the 4 pairs that are donated. Okay. So 1, 2, 3, and 4. So these 4 pairs are donated by Cn. Now since we have a sp3 hybridization, then it will have a tetrahedral shape as given in the structure. So this is the say square planar and tetrahedral. Now let us move to another structure when the coordination number is 6 here. Now since the coordination number is 6, we can both of the structure will have octahedral structure. So both of the complexes will have octahedral structure. So two kind of cases arise here. The first one is inner complexes, and the second one is outer complexes. So let us see what is this inner complex and outer complex. So what happens in inner complex is that we do not have a case of say we do not have a case of this not pairing. So we have this pairing case. Okay. So what happens is that when the ligand approaches this CO3 plus, so we are taking the example of CO NH3 whole 6 3 plus. Now whenever this NH3 approaches this CO3 plus, the electrons that are present, that are paired, so they become paired, and we have this leftover orbitals as 2d. So 2 of the d are remaining, 1s and 2p and 3p orbitals. Now all these 6 orbitals say combine and form a set of hybrid orbitals, or you can say a set of orbitals having same energy and same shape. Now we have 6 ammonia ions. Now each ammonia will donate one pair. Okay, so each of them will donate one pair, and we will have a inner orbital complex, or you can say also low spin complex. Now what is the hybridization in this case? So it is D2sp3, and it has the shape of octahedral, that is like this. Now let us take another example that is of octahedral only, but we are taking an outer orbital complex. So in the outer orbital complex there is no pairing of electron. So this is the case we have here of COF6 3 minus. So we are taking the same cobalt 3 plus ion. So we are just changing the ligand, that is F6. So in the from the previous example and from this example, you can see very clearly that ligands are of course changing the structure of the compound, and not only structure, they are changing the electronic configuration also. But this valence bond theory does not account for this say ligand species or ligand strength. That is why it is debarred, or you can say it is rejected. Now upon this combination of this sp3d2, we get this sp3d2 hybridized orbital, and now we have the fluorine which donates 6 pairs of electrons. So it also has the same shape as the CO NH3 whole 2 plus, that is octahedral. Now take a look at this table. So this table is very important for from the structure point of view. So you can have different type of coordination number, and for different type of coordination number you can have various has hybridization. So 2 has a hybridization that is linear, 3 has sp2 which is trigonal planar. Now 4 has two possibilities. The first one is tetrahedral and the second one is square planar. So we have this sp3 and dsp2. Okay. Now for 5 we have this trigonal bipyramidal which is dsp3. You should consider this thing also, that only dx square minus y square orbital is involved in this trigonal pyramidal. Okay, so this is an important point. So sometimes it asked in the exams also that which d orbital is taking part in the formation of the trigonal pyramidal, bipyramidal. Then for the 6 number coordination, we have this two kind of possibilities which we have seen as inner or outer. So this is the inner orbital complex, and this is the outer orbital complex. So the first case is for pairing, and second we do not have the pairing of electrons. So for this also the orbitals are same, that dz square and dx square minus y square. Okay, it's because the structure is same. So you can see very clearly one thing you can see very clearly here, that it does not depend upon the electronic configuration, that whether this orbital will take part or this orbital will take part or any other orbital will take part. It depends wholly upon the structure. So if it is octahedral, then of course only dz square and dx square y minus y square will participate. And if it is trigonal pyramidal, then a trigonal bipyramidal, then dx square minus y square will participate. So how do we know that why this say this orbital is only participating? So if you look at the structure of this say octahedral, you can see that we are forming like this kind of structure. Okay, so this kind of structure is formed. Now one thing to notice about this octahedral complexes is that the ligand are approaching across through the axis. Now ligands will approach through the axes, that this one, this one, this one, and this one, and this one. Now you know very well that dx square minus y square are the ligand that are oriented along the axis. This is x if this is y, and also dz square is oriented along the axis. Now due to this reason, we have this say kind of involvement of the dx square minus y square. So those who want to know the concept behind it, it is the very reason, because we know that in octahedral complexes, so you must note this point, in octahedral complexes ligands approach along the axis. Okay, along the axis. Now since ligands are approaching along the axis and we have to make a sigma bond, we know very well that sigma bonds are formed, then there will be a head-on overlap. So if ligand will come, they will come along that means that orbital will interact, which is laid along axis, and we know very well that dx square minus y square and dz square, all this two means both of this orbital are oriented along axes. That is why this both orbitals are involved in the formation of say octahedral complex. Now let us move to another part. So you know very well that valence bond theory was not able to explain the say why this inner orbital complexes are formed and why this outer orbital complexes are formed, because they do not account for the strength of the ligand. But crystal field stabilization theory, that is CFSC, take a new approach. Say rather than overlapping of orbital, they took it as the electrostatic force of attraction. So they consider the electrostatic force of attraction. Now what happens is that, so suppose these are the d orbitals of the metal. Okay, so they are in the lowest energy. So they are having in the lowest energy, means in the free state, you can say. Now as the ligand approaches them, their energy is raised. Okay, so their energy is raised. So consider this line. So this is the raise of energy. So most of the students do not take an interest why this energy is raised, because as the ligand electrons are approaching the metal, means orbitals of the metal ion, there are also electrons present in the metal ion. Now due to this repulsion, the energy of this all these d orbitals are raised by a certain energy. Okay, so this is a rise in it. Now after that, what happens is that, so this is the set of d orbitals, all the 5 d orbitals. Now they are splitted in two parts. So based on the so why is this kind of splitting happening, means why this one is getting a higher energy and this one is getting a lower energy. So I have told you earlier also that in the formation of octahedral complexes, the ligands are approaching along the axis. Now since the ligands are approaching along the axis, the orbitals which are laid across the axis, or you can say along the axis, they are raised higher in energy. Why? Because due to the greater repulsion between the electron cloud of the ligand and the electron cloud of the metal ion. Now due to this reason, they are raised at a higher energy. Okay, so this is the high energy, and in that comparison, dxy and dyz and dxz, which are between the axis, means this all these orbitals are between the axis, so they are lied below the axis. Now one thing to keep in mind is that there is a kind of conservation of energy here. Okay, so conservation of energy here. That is why if it is raised by some energy, at the same time some of the orbitals are say down by some energy, and overall this energy gap between this dx square minus y square dz square orbitals and dxy dxz and dyz orbital, there is an energy gap of delta naught. So this energy is called as CFSC energy, delta naught. So this energy is called as CFSC energy, and this is called as the barycenter. Now this orbitals are present at 3 by 5 delta naught. Okay, so this is at the 3 by 5 delta naught, means, and this is by the 2 by 5 delta naught, means these orbitals are raised in energy by a magnitude of 3 by 5 delta naught. At the same time, these three orbital are dropped in energy by a magnitude of 2 by 5 delta naught. Okay, and overall this energy, if you add both of this, that is 3 by 5 plus 2 by 5, delta naught is common, you will get a total energy of delta naught. So this is the energy gap between the two orbitals, between the two set of orbitals. Okay, now if we consider the octahedral complex here, the case is different, or you can say the opposite case arises here. So we can consider from the anomalous, so you can say consider it at the anomalous behavior, that okay, since the ligands are approaching along the axis, that is why this x square minus y square and z square orbitals are raised up in the energy. At the same time, it is raised down in the energy in case of tetrahedral orbital. This means that the ligands are approaching between the axes. Now if you look at the orbitals of dxy dxz, so suppose this is the axis that we have here. Okay, so these are the three axes I am taking. This is suppose xy, this is yz, and this is xz. Now all these orbitals, so suppose this is dxy, okay, this is dyz, and this is dxz. So these are the signs, so I'm not drawing them here. So the point is here that the ligands are lied between the axes. Okay, so the ligands are lied between the axes. Hi Anurag. That is why all these three orbitals are raised down in energy. That is up in energy. That is dxy, dxz, and dyz. Then we have this delta t here. So for this we have delta O. So this is actually delta O, not delta naught. That is energy gap for octahedral complex, and it is delta T, that is energy gap for tetrahedral complex. Okay, now this is called as T2G, T2G set of orbital and EG set of orbital. So it is written here also. It is EG and it is T2G. Now why it is called EG and T2G? Why? Because this is triply degenerate, because three orbitals are having the same energy. So it is called as triply degenerate, and this E denotes here doubly degenerate. So three orbitals are having the same energy, and this G here is for G-red. So this is a higher concept. So for now you can consider it as, so G-red is something that is having the same type of phase if we go on the opposite side. So if you consider this orbitals here. Okay, so let us consider an orbital and explain this. So suppose we have a p orbital and then we have a d orbital. So this is plus, this is minus, this is plus, this is plus, this is minus, this is minus. Now if you move from this point in this direction and in this direction at the same time, you will find a positive sign of the wave function, whereas as in this case we will have a negative sign of the wave function. So due to this reason it is not G-rayed, so it is un-G-rayed. But if you look at this compound, so if you move in this direction, that is positive. If you move in this direction, it is also positive. Now for this it is negative and it is also negative. So this is having a G-rayed type of means G-rayed type of shape. Now this octahedral complex is generally G-rayed in nature. Why? Because it is highly symmetric. So you can see very clearly that this octahedral complex is symmetric in nature. So if you move in this direction and if you move in this direction, you will find the same kind of structure. So it is, we use this G here, and for this tetrahedral complexes, you know very well that they are not symmetric in nature. Due to this reason, there is no G written here in this case of tetrahedral complex. So this was all about the splitting of the say splitting in the CFSC. Now for some reason, so if I want to say that some reason, I can say the reason number one is that the number of ligands that are approaching in case of say d orbital is in case of this octahedral is more. Due to this reason and many more reasons we have, I will not consider that. So you can keep in mind that delta t is 4 by 9 of delta naught. That means delta t is less than delta naught. Okay. So this is the case that delta t is less than delta naught, and this relation is very important. Okay, so you should keep this in mind, that delta t is equals to 4 by 9 delta naught. So I will not getting means looking at the derivation right now. So it is a short derivation. If you want, you can refer to internet also, but it's not important from the examination point of view. So I'm not doing the derivation. So questions are asked directly from here. Okay. Now let us move to this low spin and high spin complexes. So what is low spin and high spin complexes? So before that, we will consider the strength of the ligand. So we have seen that in the VBT, we are not considering the strength of the ligand, but in case of in case of this CFSC, there is a series called as the spectrochemical series. This series is mainly about the strength of the ligand, that different ligand have different strength, and this ligands have only the power to increase or decrease to, sorry, these ligands have the power to increase and decrease the delta naught or delta t. Means for octahedral it is delta naught and for tetrahedral it is delta t. Now what happens is that they have a higher say splitting strength. So if we start from here, then this is the area of, you can say, weak ligands. Weak ligands. You can consider this as a boundary line because this is not a strong nor neither a weak one. This is a border line. And these are the strong ligands. So these are also in the border line. So from here to here, it is the kind of border line. They are neither strong nor weak. And after this, we have this strong ligands. Now what happens is that we can arrive to two cases. So if this delta naught is greater than pairing, okay, so we will have a low spin complex. So we will see what is low spin and high spin during when we solve questions. So we will see them. And for delta naught is less than p, we will have the high spin complex. Okay, same thing is written here. Sorry, I have repeated it twice. Now what happens is that say we have this we have the structure here. Okay, so we have the structure here. Now what happens is this is the delta naught for this plating. Now ligand have a say pairing power, means if they are weak ligands, their pairing power is low, and if they are a strong ligand, their pairing power is high. Now for a strong ligand, their pairing power is such high that the electrons cannot move from this orbital to this orbital, and a kind of pairing takes place, means the electrons are paired in the lower orbitals only. So suppose this is the dxy, dxz and dyz. So if you draw it here, okay, so if you draw it here, so we have two orbitals on the upside and three orbitals on the downside. Now the case happens is that if we have d4 configuration, we have now the electron starts to fill. So we can first of all fill this singly filled all these three electrons in the three orbitals. Now where will this fourth electron go? It will depend on the strength of the ligand. So if this ligand is very strong, that is delta naught, that is the energy gap between this delta naught is less than pairing, means the pairing energy is high. Okay, so if the pairing energy is high, okay, so this is the pairing energy. If it is high, then it will go to upside, okay, and it will form a high spin complex. High spin complex, meaning that if you want to pair the electron, it is requiring more energy rather than to move the electron to upside, because pairing energy means if we put an electron, that how much energy is required, and if it is greater than the delta naught, then the electron will not go and pair here, and it will go to this upper orbital, and it will form a high spin complex. Contrary to that, if you have another case, okay, so this is the next case we have, that delta naught is greater than p, means it is difficult to move the electron to upside rather than to pair it. So what we will do simply is we will pair it, and this for the same d4 we have this configuration that is called as low spin complex. Low spin complex. Now we cannot consider only the say strength of the ligand as the final deciding factor of this pairing and not pairing, means up to much extent you can say you can cover the most of the complexes using the strength of the ligand, but there are various other factors that depend that changes this delta O. So the first factor is the say strength of the ligand. The second factor you can say the charge on the charge on the metal ion. Now what is this effect? So I have told in the starting phase only that CFSC is mainly a theory that is completely based upon the electrostatic force of attraction. Now if a metal ion has a greater charge, greater magnitude of positive charge on it, there will be kind of greater force of attraction. Now due to this, the splitting will happen in a more wider way, means the delta O will be increased if the charge on the metal is increased. Okay, so the first factor that we have here is, so this is written wrong, sorry. Okay, yeah, it is right. Okay, so if we have this delta O, that is pairing energy is more, then the electron will go to upside and we will have a high spin complex. Now, what I was saying is that the say we have the two conditions. The first one is the strength of ligand. So the first factor is the strength of ligand. So let me write it on a board. The second factor is charge on metal ion. So as the strength of ligand will increase, the delta O will increase. Similarly, if the charge on metal ion will increase, this delta O will increase. So for now, you can consider the two cases, that is strength of ligand and charge on metal ion. Okay. Now let us move to some questions. So I'm not discussing this theory of magnetic field and say color in the theory. I will just solve some questions and you will get a grasp of this ideas very clearly from the questions only. Okay. The first one is that the structure of which of the following chloro species can be explained on the basis of DsP2 hybridization. Okay. So the question is basically here is that which one is explained by the basis of DsP2 hybridization. So although Cl minus is a weak ligand, okay, but this Pd will form a low spin complex. Why is it so? So the reason is that, okay, so let me make a point here. So we have this three series: 3D, 3D, 4D, and 5D. So this 3D case have a case of high spin and low spin. Okay, but for 4D and 5D, all of the complexes that are formed, they are generally, I am saying the word generally, there may be some exceptions, but they are generally low spin complex. So what is the reason behind is that because this orbitals of this 4D and 5D are very diffused. So you know very well that as we move down the periodic table, the shells or the orbitals are getting away and away from the nucleus. Now due to this reason, they cannot maintain the shape. Means if you are seeing at the shape of something, it generally happens due to the force of attraction. Because if you want to look it in a more brief way, so if you have a solid, then the force of attraction between the particles keep it intact. Now compared to the gas which is having less force of attraction, they are diffuse, or you can say they are moving away from each other. Now if you apply that similar concept to the orbitals, now as the orbitals are moving away and away from the nucleus, they are getting more and more diffuse, or you can say they are more and more having a irregular shape. Now due to this reason, since they are diffused, they are say when a ligand approach them, they are say delta O becomes larger and larger. Okay, so you can consider another concept is that, so first was the strength of the ligand. So as the strength of the ligand increases, the delta O increases. The second one is that as the charge on the metal ion increases, the delta O increases. The the third factor we have, that as we move down this transition series, that is from here to here, the delta O increases in this fashion. Now as this delta O is increasing, therefore the pairing energy is not that much, means it is the delta O is increasing, you can say. So delta O is greater than pairing energy. So rather than say pairing of electrons, so pairing of electron takes place in 4D and 5D series. Okay, sorry, delta O is increasing. So I'm just I want to make the point here is that 4D and 5D series compound forms low spin complexes generally. Okay, you can keep this in mind. So it is forming a low spin complex also with this Cl minus, which is a weak field ligand. Now due to this reason, the we are having a dsp2 hybridization. So we have this inner and outer complex. Okay, inner and outer complex. Okay, so inner means low spin and outer means high spin. Okay, so this is a general analogy from both of this VBT and CFSC. So they both are the same thing. So do not get confused with it. Okay, so this is the reason we are having a kind of a DsP2 hybridization in PDCl42 minus, because all this remaining iron, cobalt and nickel are from the 3D series and their delta naught is higher. So delta naught is lower. Sorry. So if delta naught is, so if pairing is lower, okay, so the pairing is higher. Okay, so pairing is higher than delta O. So due to this reason, we are having a say a high spin complex. Now moving to next question, which of this is diamagnetic? So we will see all of these structures, means all of the bonding and anti-bonding and valence bond theory, and use this to predict the magnetic behavior. Okay. Now I have told you that I am not teaching it, so we will deal it with questions only. So first of all, we have this FeCN6 3 minus. Now this both Fe3 plus and CO3 plus have unpaired electrons. So how is it so? So if you look at the Fe3 plus, it is having a configuration of 3d5. So although you pair it, it will form only two pairs and one electron will be left. So we do not have to see the electronic structure or do not have to see the ligand. We can just see it from their say from their number of electrons in the outermost shell. Now moving to D6, it can be paired and it is of course paired because C2O4 minus is a strong ligand. Sorry, it is a borderline, it is having a borderline. So now it will depend upon the charge on the metal ion. So generally for the border ion means borderline ligands, if we are having a charge of 2 plus, then it will form a high spin complex. And if we are having a charge of 3 plus, then we will form a low spin complex. So this is for the borderline ligands. Border line ligands. Now it will form a low spin complex. So all of the electron will be pair, or you can say inner orbital complex, and we will have a diamagnetic behavior. For this case, we will have a paramagnetic because one electron is not paired. Okay. Now we have to find the magnetic moment. First, we have seen that how we can say that whether it is paired paramagnetic or diamagnetic by looking at the electronic configuration. So if we have a say unpaired electron, then we will have this paramagnetic behavior, and if it has a unpaired electron not present, then we will say it as diamagnetic. Now how we will decide the magnetic moment? So we will take the case of NiCl4 2 minus. Now NiCl4 2 minus, this is the compound we have. So let me make it clear here that for tetrahedral complex we do not have any case of low spin or high spin or inner orbital or outer orbital. So we simply do not have this pairing of electron in this tetrahedral complex. So it will always be remain unpaired. Now we have this sp3 hybridization, that is this one. Now we have two unpaired electrons. So the formula that is used to calculate the magnetic moment is n into n plus 2, where n is the number of unpaired electrons. So you will simply put all the values and you will get it as 2.82 Bohr magnetron. Now we have another question here that we have to find the magnetic moment. So we have the three ligands. Okay. Now let me clarify here is that if we have one ligand, one strong ligand only, then we will have a pairing of electrons. So you should keep this in mind. So suppose we have multiple ligands that are present in a complex, and if you see that there is a strong ligand, one strong ligand that is present, then it will simply pair all the electron of that compound or the complex. Now we have this Cr plus. So if you see the oxidation state, you can find it from here. It is 1, it is 0, it is -4, then total of 2 negative. So 4 minus 1, 3, 3 minus 2, that is +1. So we will have a +1 oxidation state of Cr. So it will be 3d5 4s0. Now since I have told that if one strong ligand is only present, it can pair up this. So we have this Cn minus as a strong ligand, so it will pair all the electrons, and we will get it as this electronics configuration finally. So the formula is n into n plus 2, that is 1.73 Bohr magnetron. Now we have to see that which of this ligand has the maximum magnitude of delta naught. Now if you look at this question, first you will see that which has the what oxidation state. So it has +2 oxidation state. So this is having a 3+ oxidation state. Okay. Now this is having a, so C2O4 2 minus, C2O4 minus, so that will be 3 minus, so it will be +6. Okay, this is also +3 oxidation state. So I think C2O4 2 minus. Okay, so C2O4 2 minus, that is 6 minus, and 3 is remaining. So it is also having a +3 oxidation state. Now if you want to look at the delta O, then first of all consider that which is the complexes which is having the lower charge will have the lowest delta O. Means the strength of ligand is of course say criteria for defining the magnitude of this delta O, but this charge on metal ion is a greater deciding factor, because if we are say deciding the spectrochemical series, then just we are seeing the electronegativity thing and all, and in electronegativity there is kind of partial distribution of charge. But if you look at this charge on the metal ion, then it is a complete positive unit positive charge. So an increase by a plus unit positive charge, +1 unit positive charge, means that there is a greater effectiveness of this say charge on metal ion. Now we will see these three. Now since all the three metals are same and the charge oxidation state is same, now we will consider the we will consider the strength of the ligand. So if you see here that out of this three, this Cn is having the highest strength of all this. Now due to this reason, it will have the maximum value of delta O. Okay. Now which of the color of the coordination compound depend upon field splitting? What will be the correct order of adsorption of wavelength in the following complex? So from now I will not give you answers, I will just give you a hint of this. So it is saying that which will have a order of adsorption we have to decide for the wavelength of light. So which will have the lowest wavelength and which will have the highest wavelength. So if you consider the formula, we have that E is dependent upon H C by lambda. Okay, so C by lambda, 1 by lambda. That means E is inversely proportional to N. Now if you are absorbing say energy in this, then the energy gap is dependent. It means it will depend on the energy gap. So if you are having a higher energy gap, that is delta value, that means we are having a lower 1 by lambda. Means the order of delta naught, if it goes in this order, so if it increases in this order, then the value of lambda will decrease in this order and increase in the opposite side. Means the one that is having the highest delta O will have the lowest lambda. Now you have given you the hint, you will just compare all this delta O value of all these three complexes and one which is having the blue and blue. So for those who do not know, we have this Vibgyor. Okay, this has this Vibgyor, and it is having the highest energy. So this is having the highest energy, and energy increases in this fashion, meaning that red has the highest energy, then we have this yellow here, then we have this green here, and then we have this blue here. Now which will have the lowest energy, which will have the highest energy? This violet, or you can say this blue, will have the highest energy. So it will have the highest energy. That means it will have the highest strength of the ligand. Now, this is the blue. Okay, so L4 is having blue. L4 is having blue. That means it will have the highest energy. It is absorbing the blue light, so it will have the highest energy, L4. Then we have this Y, that is yellow. So before that it is green. So they have this blue and this green. Okay. So green is related to L3, L2. So then we will have this L2. Then this yellow is related to L3. Then we will have this L3. So I solve this question. We have this L1. So if you compare it, so we have this as the answer. This is the correct answer that we have. Now let us move to next question. So what does this question says? Which of the following statement is incorrect? So Fe3 plus iron also gives blood red. So you can solve it by yourself. It is just a theoretical question, so I'm not giving any hint to it. Now this is a good question that we have here. The value of CFSC for the complex is itna. That is 1800 centimeter inverse. The CFSC for COCl42 minus complex is. So what are we seeing here is that we are having the same metal ion, we are having the same ligand, we are just changing the coordination number from 6 to 4. So simply you will use this formula which says that delta T is equals to 4 by 9 delta naught. We have this value of delta naught here, that is 1800, and we will put this value and we will get our answer. Whatever the answer comes is the right answer. Okay. Now next, the value of CFSC for the complex is itna. Oh, sorry for repeating the same question. This is the same question that we have seen earlier. Okay, so that was for today's class. So you can ask question if you have any. Okay.